XPS imaging can be used to diagnose problems with data taken from an XPS instrument. And in this case we're going to show how a sample where charging effects alter the spectra, and by using XPS imaging we can work out why the spectra were different. So we're going to begin by performing some outlier filtering on these data. That's to say, we're going to try and reduce the influence of noise by going through the data set and altering pixels when you find an abnormal intensity compared to the average of pixels. So having done that, I'm going to copy the processed data. So I preserve my processing as a new VAMAS file, and then I can return the data to the original state. And what I'll do next is I'll convert these images to spectral pixels so we can see what they look like. And although you can see some kind of structure in here, it's really not going to give us any clues as to what's going on a pixel by pixel basis based on spectra like these. So we'll go back to our data set in image form and look at the processed form, and the very first thing we'll do is we will use some predefined patterns that we can use to sum the data. And if I want to see these predefined patterns, I can look for the pixel mask, and you can see the pattern that I've got right now are strips of horizontal pixels that are going to be associated with each other, and we can sum spectra from these strips if we wanted to. Or I could go through and look for the next one. Those are vertical, those are concentric squares, and that's the pattern that I'm interested in. We've got a checkerboard, and if I go back to my spectra and sum spectra using colors, I will get 16 spectra, and these give us an indication of what's happening in different positions in this image. And you can see straight away by zooming in to this carbon peak. Let me just put it binding energy again. So this is the carbon peak, and you can see that while the majority of these spectra all have a similar sort of binding energy associated with the carbon, there are some that are not. And what we need to do is work out what it is that's gone wrong and where in the sample it's gone wrong. So let's go back again, and this time I'm going to set the false color here, and we will do a PCA type calculation on these images, and there are 605 images here, 64 by 64 pixels. The reason I've got 64 by 64 is for the video. It's competing with the acquisition of the video, so I would normally do this with a better pixel resolution. But I can already see here, that's the first abstract factor. The second abstract factor, this is partitioning in a way that is unexpected for this sample. This sample is not expected to have anything other than a uniform chemistry, so to see a structure like this as the second abstract factor is unusual. So let's put on a histogram. So I'm going to mark up a position there. I'll turn off the automatic limit calculation so that it's using the range that I specified with the cursor, using this color scale, the pixels that would be identified by these two limits. And what I'm going to do is mark those up as a color, and I'm going to use one color to mark all of these pixels. So this is one phase that I'm interested in, and the next phase I'm interested in is what's up here. So let's just mark out using the color scale arrange, and so now I've got pixels colored red and I've got pixels colored black, because all we're interested in is summing spectra from these pixels and spectra from these pixels, and to see what the differences might be between these two zones. So I'm going to go to the image processing. I'm going to define the image using this mask that I've got defined. And now if I go to the spectra pixels and I sum these, I get two spectra rather, and I can see that there's clearly a shift. So there's evidence that this sample is certainly charging. Now let's actually do a little bit more than simply see that there is a shift. Let's see how the shift is performing overall. So I've gone to the energy calibration. I'm going to hold the control key down so I can move this spectrum, the black spectrum, over the red one, and then press apply. So I now have an energy calibration, and I've calibrated on the carbon, so you can see that pretty much there's a similar, reasonably similar energy calibration for that chlorine peak. If I now have a look down here at the lower kinetic energies, we can see that there's a shift. Even though I've got a calibration based on the carbon, I've got a shift in the oxygen peak. Let's do the same thing again and shift the oxygen peak so that it looks like it's calibrated. We can see that the oxygen and the titanium look reasonably well aligned, but we now have a misalignment up here. So not only do we have a different charge state, we have potentially got a sample here where one part of the sample is continuing to charge differentially over the length of the experiment.